Okay, so the next step in the analysis will be to evaluate whether a gene is differentially expressed in the two conditions. So we have a few animals, here 4, in the condition control. They are not affected, they are healthy, they are fine, everything is good. And we measure the expression levels in these 4 animals, and in the first one is 54 each, the second one is 49, the third one is 38, and the fourth animal is 66. Now please notice here that all the time we talk about the same gene, gene 1. And then we have 4 other infected animals that also we measure the expression level of the same gene. Now the number of the animals in the two classes does not need to be the same, so the number of animals in control can be different, so it does not need to be the same as the number of animals in infected class. Here we have 4 and 4, but in general this number might be different, okay? So we measure the expression level on the infected animals, and we find the first one 99 reads, the second one 102 reads, and the third one 134 reads, and in the fourth one 65 reads. Now the question is, if the infection caused a differentiation of gene 1 levels. By eye here we observe that okay, it might be different, it seems to have higher values here, even though we have some overlap. For example, in this control animal we have 66 reads, and in this infected animal we have 65 reads, which is lower than 66. So even though we might have some overlap, we observe that okay, this seems to be bigger in this category. What I will show below normally, I must say that, normally is correct for the microarrays analysis. And not for RNA-seq. However, it's much easier to understand differential expression in this context, and later on we will extend this for RNA-seq data. Still, you can apply this methodology for RNA-seq data. However, you may miss some differentially expressed genes, or you may find some false positives. But in any case, you can still apply this methodology that I will explain here for RNA-seq. Okay, so this was a disclaimer. Now, if I will take these 4 values that belong to the class control, and these 4 values that belong to the class infected, and I put them in a graph where on the x-axis I have the class control and the class infection. So the 4 expression values are here, and for the class infection the 4 expression values are here. We observe what we said before, that in general it seems that the expression values of the infection class is higher than the expression levels of the control class. And of course there is some overlap. We observe that this value is greater than this value. Okay, and the question is, if infection causes a different expression value in gene 1, so this gene 1 expression, not in general, compared to the control. And we might see different answers here. So the first answer is no, because there is some overlap. Since this value is higher than this value, it means that sometimes in the control class we might get an expression value that is higher than another value in the infection class. And since this happened, then okay, we should say that infection does not really makes expression value to be higher. And obviously this is, or not obviously, but this is not a correct answer. Okay. The second answer would be, you should evaluate the mean values. So let me get the mean. The mean value here is somewhere here, the mean value here is somewhere here, and since this is different and mean of the infection value is much greater than the mean of the control value, then we should say that the expression levels are different and the infection causes expression value to be greater than the control class. This is partially correct, but again it's wrong, because what we have not taken into account is the variances within each class. So this might be bigger, but there is some variability here, and if, for example, the variability would be like that, so here are some other expression values, hypothetical experiment, and here are some other expression values. Again, the means are the same, just the overlap is much greater here. Then in this case we might have said that the expression levels are not actually different. So this brings us to the third point, which is actually the correct answer, and we should say maybe, but in order to decide whether infection causes a change to the gene expression level of gene 1, we should apply a statistical test. Now the point of the statistical test is that we will compare the means, but we will take into account the variances of the measurements within each group, in the control group and in the infection group. And now you can understand that since we will take variances into account, then we should have several samples here and here in order to estimate as accurately as possible this variance of the measurements. Definitely we cannot do it with one sample, because we need at least two samples to estimate the variance. And in general, the more we have, the more accurate we are, or in other words, the more samples we have in each class, the smaller differences we might be able to detect. Okay, so what are the important measurement and facts when we apply statistical testing? A statistical test to assess whether these two expression levels, whether this condition, the control and the infection, have different expression levels for a particular gene. Two things are obvious from this picture. One is that the mean values should be different. So if these are different, then it might be that the infection causes a change in the expression level compared to the control. We will see some counterexample on that, but in general this is correct. So an important measurement that we should take into account in order to evaluate whether infection causes some change is the mean values in these two groups. And this, since we want to take this into account, what is important for us is this difference. The difference between these two means, which either is μ1 minus μ2, if this is μ1 here and this is μ2, or μ2 minus μ1. Okay, so the difference between means is important. The variance within each group is important. and I explained that a little bit earlier. If we have big variances, then it might be the case that the factor here, the infection or the control, does not actually causes a change that we can detect with our sample, just because the variability of the measurement is so great within each group. And the third thing that is not so obvious is that in order to apply the test correctly, the data should follow approximately a Gaussian distribution. So in theory, a Gaussian distribution is required. Gaussian is another name for the normal distribution. However, in practice, even if the data do not really follow a Gaussian distribution exactly, then it's still fine. Now, okay, you might wonder why Gaussian is important, and let's see some examples to understand why it's important. Here I have again the control class and the infection class, and the expression values in the control class are distributed like that. So I have some values around the mean, and then I have a few outliers here, and the mean is μ1. Now the mean expression value is the same for the infection class. However, the distribution is dramatically different. I have now two groups. One has much higher expression value than the mean, and the other has much lower expression value than the mean. So still μ1 is very similar to μ2, and in this example it might be also that the variances are similar, but clearly infection causes changes to the gene expression profiles. So in this case we would say actually that if we could compare the means, that infection does not cause any change to the expression value. However, in reality we see that it causes something. Now this is a case that we will miss this differential expression profile because we assume that the data should have a normal distribution here. If we would like to do it properly, what may happen here, what might have happened here is that there is some other factor, for example infection from a different bacterium, that some of them, some expressions are very high and some other expressions are very low. Or there is some other factor like the gender of the infected individuals, that for example infection causes the female individuals to have high expression level, and infection causes the male individuals to have low expression level. Clearly there is something strange in the infection class, and this makes data to not follow the normal distribution, and it causes a problem in our inference. Another example is here, that you see that in the control class and in the infection class most of the values have a low expression value, are low here and here, but in the control class we have many outliers that causes an increase of the mean value. And then if we apply a statistical test, we might find that this difference is quite big, so this gene might seem to be differentially expressed because of the infection, so to have lower expression value in the infection class, whereas in reality it's all because of these outliers here. So again, we have an example that data do not follow a normal distribution. We find differential expression, but this might be because of the fact that we assume that the data follow a normal distribution, whereas in reality they don't follow. Okay. So these were two examples just to demonstrate that it's important, or relatively important, our data to follow more or less a Gaussian distribution. Again, I will say that it's not very strict. even if there are some deviations from the normal distribution, the test that we will discuss now is accurate. However, in some cases we might miss genes that are differentially expressed and we will say that they are not, or we might find genes that are differentially expressed whereas in reality they are not. So we must be careful. And since I said that, I should say again this disclaimer that for RNA-seq data, they are not actually distributed according to the Gaussian distribution. So we should apply a different test, not the one that I will describe here. However, it's much easier, I think, to understand the concept of differential expression in this framework, assuming Gaussian distribution and Ttest, as we will see now, than the generalized version that we use in RNA-seq data. Okay, so if everything is okay with the data, then these plots here guide us to use the following statistic to be able to measure this differentiation between the two classes. So again, we have control and infection, we have these 4 values here and the 4 values here. And what seems to be important is, of course, the difference of the mean. Me1 minus me2, or me2 minus me1. It's not, doesn't really matter so much which direction we will put here. And the bigger this difference is, the easier for us is to decide that this that the infection causes this gene 1 to be expressed differently in infection than in control. Which means that if I want to build a single measurement to evaluate the effect of the infection relatively to the control, then this difference, me1 minus me2, should be in the numerator, because a big value here, a big positive value or a big negative value, will imply that infection causes this gene to be expressed differently. So again here, when me1 minus me2 is very positive or is very negative, then we might say that we have an effect due to the condition here. The second thing is the variance. So again, let's assume the following. It's more difficult if the data have big variance in each group, like that, to say that they are differentially expressed, even if their mean values might be exactly the same. So compare this case where the variance is big, the me1 is here and the me2 is here, the average of all these values is somewhere here, but the variance is big, the overlap is huge, and compare this case with another case which is like that. Now the control class is distributed like that here. These are all the values, and the infection class is distributed like that around the mean. The blue and the red cases have exactly the same means, but the variance is so dramatically different that it's very clearly in the red case that the gene is differentially expressed in the two classes. So the second case is, the second important measurement is the variances, and because small variances means that it's easier for us to detect a differential expression, it means that the variances should be in the denominator. here. When these numbers are small, the variances are small. So when the variances are small, the whole fraction here becomes large. So this T-statistic obtains a large value, and it guides us to the direction that there is differential expression. And okay, let's see that together now. When this difference is big, either positively big or negatively big, and when this is small, both of them have as an effect that the value of the T-statistic is large, so we might be able to detect differential expression. Okay, this intuitively seems very clear, I think, and now the problems start. How much positive or negative the T-statistic should be to say that there is differential expression? For example, if it is 0, then okay, we will say that there is no differential expression. What we will say if it's 0.1? Or what should we say if it is 0.9? Or what should we say if it is 10? Or what should we say if it is minus 10? What should we say if it is 5.6? And so on. Clearly there is no a clear threshold, and all these values are quite arbitrary in order to decide whether we have differential expression or not. We should have some process, some procedure that will help us to decide whether the value is big enough, either positively or negatively, in order to decide that we have differential expression. And this procedure is actually formed very nicely with the hypothesis testing. And there are two concepts in the hypothesis testing. One is the null hypothesis and the other is the alternative hypothesis. So the null hypothesis claims that is what we usually say, let's assume that infection and control have the same expression values. On average, or in other words that or me1 equals to me2 or me1 minus me2 equals to 0. Okay, why this is helpful? Because then we are able to do the following trick. If in order to decide whether a T-statistic value is big enough to tell me that I have differential expression, I think as follows. If I could get the value of the T-statistic when there is no actual difference between the two populations, between the control and the infection class, then what values of the T-statistic I would get in this case? Okay, I repeat that because this is the key in this procedure. If I would assume that there is no difference between the control and the infection class, so on average the expression value would be different, would be the same, but of course in reality we will get some differences because of sampling. Now if I would assume that there is no difference between these two classes, what value of the T-statistic I would observe there? In order to understand this, let me make a small plot here. So I say that let's assume that control is the same as in the infection. So that for gene 1, doesn't really matter if you are if you really belong to the control class or to the infection class. Does not really matter if you are infected or not. Now, if this is the axis of the expression value for gene 1, and we have assumed already that does not really matter if you are control or infection for gene 1, so gene 1 is not affected actually, then I will use the black color here to point out where some expression values for the gene 1. So for example, this is a value 10.1, this is a value 11.2, this is a value I don't know, 12.1, this is a value 14. And these are the guys, the individuals that are in the control class. So the black is control. And again, gene 1 is not affected, right? And with red, I will use the expression values for the infection class. So infection is red. And since gene 1 is not affected, I might get these values here. So let's put some 5 individuals. So this is 9, this is 10.8, and so on and so forth. And the last one is 14.2. And this one is 12.3. Okay. If I will get now the averages in this case and the variances in this case, I may calculate a value T1 of the statistic, which will be μ1 minus μ2. I calculate the mean values and I divide by the variances, which will be sigma 1 square divided by n1 for black guys minus, I should have taken black here, doesn't really matter, 2 here and n2 here. So I can calculate this value, which will be a number, and let's say that this number is yeah, let's put some numbers here. Let's say that the red one is, the average of these values is 11.3 minus the average of these values, or the black values, is 11.5, and then I must calculate these things here again, and I will have some number here. Let's say that this number is 0.9, so approximately this number will be something like minus 0.22 or something like that. Okay, it's clearly this number is different than 0, but is it big enough? We have assumed that this is the case when there is no actual difference between the control and the infection. If I would repeat this analysis many times, and I will repeat this experiment many times for genes that are not really affected by the expression, by the infection state, so if it is controlled or infected, then I would get several values here, and all these values correspond to a hypothesis or to a reality that we have no effect of the condition. So this means if you are in the control class or the infection class on the expression level. And this will be many numbers here. Let's say that these are the numbers that I have: 0.5 minus 0.22 minus 0.8, 1.3, and so on and so forth. And I can get all these numbers and make a plot of their distribution, which will be around 0. Sometimes I will get high values, sometimes I will get very low values. Now this is the distribution of the T-statistic for the cases that there is no actual difference between the control and the infection class, or in other words is the distribution of the T-statistic under, and I use this pipe here, under the null hypothesis. Now why this is useful? It's useful because if in reality I will find, if I know this distribution, but in reality I find the value of the T-statistic that is, let's say, 4.1, you see it's much greater than this one. Even if theoretically it's possible to find the T-statistic when the null is true, in this case that is greater than 4.1, so all these cases, which will be a few cases here, have a T-statistic that they have a value greater than 4.1, even though there is no effect of the condition. But this probability is very, very small. The probability for this to happen is very small. The probability to find or to get a t value when the null is true, the probability to find the t value when the null is true that t will be greater than 4.1 or equal is very small. So, okay, now we are guided somewhere. We have seen how the distribution of T-statistic is when there is no effect of the class on the expression value, so when the null hypothesis is true. And we have an observation that is 4.1, and this observation is much greater, is quite great relatively to what we get when the null hypothesis is correct. Still, we might get some values, a few values, that the T-statistic value is greater when the null hypothesis is true, but this probability to get such a value is very small. Then we say that now if this probability P is smaller than 0.05, so smaller than 1 out of 20, then we say that we reject the null hypothesis and we accept the alternative. We accept that the condition has an effect on the gene expression level. Affects the expression. Okay, let's go back to the previous page here. So the important thing why we have to do all this mess is because we need to have an idea about the t values when there is no actual difference, no differential expression. Because if we would know this, then we would be able to compare these values when there is no actual difference to the observation that we have, and if our observation is very positive or very negative, then we could say that the condition affects gene expression. So for example, in this case, we would say that we have an effect. In this case, we will say that we have an effect of the condition of the gene expression, but in this case, we could say that there is no effect of the condition on the gene expression levels. Now this is obvious here because what this picture here tells us is that it's not so difficult to get such a t-statistic value when the null hypothesis is true, which means that it's not so difficult to get such a t-statistic value when there is no actual difference between the control and the infection class. In reality, we get so many values that are greater than the observation, and this probability might be quite large, like something like 0.4, 40%. 40% of the values are greater than our observation when in reality there is no difference between the infection and the control class. So even if the t-statistic is not 0 but has some value, let's say 0.3 here, then this value is not big enough to tell us that the control and the infection class affect differently the expression value of the gene. So this is the whole point of differential expression analysis using the t-statistic and the t-test. So there is a test based on the t-statistic, which is called t-test, that calculates the value of the t-statistic and then calculates exactly this probability, and if this probability is smaller than 0.05, then the conclusion is that we reject the null hypothesis, we accept that there is differential expression, but if this probability here is greater than 0.05, then we say that we cannot reject the null hypothesis, we accept the null hypothesis here, there is no effect of the expression of the condition on the expression value, and here we reject the null hypothesis in the previous case. I hope all that is clear, and later on we will see how this is extended for linear models.